Hello folks, welcome to a new video. So in this video I mostly want to discuss about CPU intensive and memory intensive operations. So the basic purpose of this video is to build, let's say, a sort of an intuition on when you see some lines of code, you should be intuitively able to sort of predict if it's consuming more CPU or consuming more memory, so that you can optimize for that if it's required and such and so on. Right. So from the basic understanding or from the bookish definition of CPU intensive operations, anything that requires a lot of arithmetic calculations is CPU intensive, and anything that consumes a lot of memory is memory intensive. Right. So let's look it from a human's perspective. Let's say you are asked to calculate the multiplication of 69 and 420. So that's an arithmetic operations. That's a multiplication operation. So when you're asked, you will take some time, you'll calculate it, and then you'll tell the answer, right? But it's not like you have to remember the answer or you have to come up with it on the go itself. That's not possible. If you don't remember the answer, of course, then you have to calculate it. But you can come up with it. So that's a calculation. And so similar context you can take in context of a CPU. It's a calculation, so it's a CPU intensive operation. It's not intensive as such because it's a simple operation for a CPU, but it takes up more CPU than memory, let's say. And for memory intensive operations, from a human's perspective, let's say someone asked you what's the capital of some XYZ country, right? So if you know, you can tell the capital instantly, and if you don't know, you cannot. So that depends totally on your memory, like how much you can remember. So similar sort of thing we can translate to a computer. Let's say a good way to think about it can be a key value pair, right? So the key will be your country name, the capital that you are asking for, and the value will be the answer, right? So whenever someone asks you the country name, you can scan through your key value set, you can get the element, and you can return it. And if you don't have it, nothing, you can't do anything about it. That's done. So that's the basic intuition here, that basic intuition where which you can, let's say, visualize the memory and CPU operations in your day-to-day scenario, right? So let's take an example of it. Let's take an example of something that consumes a lot of CPU. So here I have a small bash script written which monitors the CPU and memory uses, right? So I'll just walk you through the bash script once. So what it does is it's an infinite loop, and it takes the CPU, takes the memory, whatever is used, and then clears the screen, and it shows the CPU and memory, right? So that's what. And it runs in interval of 1 second. So every 1 second it refreshes how much memory my system is consuming, how much CPU is consuming, and it shows that, okay, so that's what it does. So it's running an infinite loop. On every 1 second it refreshes the value, and it's showing it here. So currently I'm approximately, like, my CPU is approximately, my PC is approximately consuming 39% of almost 40% of memory, and CPU is almost zero, nothing as such. So let's try to run something CPU intensive. So I have a program written here for a Fibonacci series, to calculate a Fibonacci series, and I have this, right? So it's a very simple program, so nothing complex as such. We have a function here, and we are passing a parameter n, and we are calculating the value of n minus 1 and n minus 2 recursively, right? And we are adding them and until we reach n, and when we reach like the last value, that is greater than n less than equal to 1, then we return it. That's what. So it's a simple program, but the thing is, you can see we are not using a lot of data structures and stuff here, right? So not always, but intuitively what you can think of is there is just like you're not assigning any variables as such, and anything that takes up memory. This will take up memory, of course, but it's more inclined towards being a CPU intensive operation than a memory intensive operation. Memory, everything will take, that's inevitable, but we are talking about the intensity of it, right? So it's mostly CPU intensive because it has a humongous number of calculations. If you do for 40 itself, let's run this program, and we are just timing how long it might take. Like I'm doing console.time CPU intensive time n, and it will show up amount of time it takes to compute. Let's say how much time it will take to compute. Let's say 43. Let's say 43. Okay, let's try this. So here, just keep an eye for this, right? So to validate if our theory is correct, if it's a CPU intensive operation, your CPU usage should increase, right? If I can speak properly. So yeah, let's start it. So it's calculating it. Okay, I think 1 second was not a good frequency. Maybe I should minimize this. Maybe I should do 0.5 or something. 0.2, let's say, because it does this in like 3 seconds. So it's refreshing now almost every 0.2 seconds or so. So let's make this 45 this time and see if it changes. So you can see it went up 5%, 6%. It's going up, right? 12%, and it came down. It's back at 3%, back at 0%, and so on. And it took us approximately 9 seconds to calculate it. So you saw the spike in the CPU usage, right? So let's say we run it again. Let's see what happens. Your CPU 1%, 20%, spiked up 19%, and it will eventually come down once it's done, and it went back to 0%. So basically it took the CPU it required, it did the calculations, it returned the value and released the resources, whatever it was consuming, and it took us about 9 seconds to calculate this, right? So this is on the CPU intensive extreme of it. Like if you imagine two extremes of something, if it's the memory intensive, it's the CPU intensive, these two sides are supposed to be inefficient by default because those are the two extremes of it. Your ideal good approach as such, which is a very subjective thing, but let's say anything that you build, it should not consume too much of board, it should be somewhere in the middle. So yeah, so my basic purpose of this video is to build an intuition regarding that, so that you can think about what can be optimized, because ideally if you are like, okay, my program works, it's fine, this also works, nothing wrong with this, right? But it's taking up a huge amount of resources. And other than that, if you are talking about JavaScript, it's single threaded. So that's another problem with JavaScript. Not problem, I mean, that's the language choice, I'd say. Like, but still, there are many things that you can do, I think, like web workers and async and so on, but still it's, at the core, it's a single threaded language. So if your CPU has 1 core, if your CPU has 8 cores, doesn't matter. It's a single threaded, it can use only 1 thread. So that's what. So you need to be very careful about CPU uses in JavaScript, otherwise it will block your whole flow of operations and stuff. So yeah, that's this approach. Now let's move on to memory approach. What am I speaking? Let's move on to memory intensive operations. So what will be a memory intensive operation? So whenever there is something that takes up a lot of memory, a lot of your RAM and something, like that will be a memory intensive operation, right? So let's say you have a array, the thing we have in JavaScript, it's not really an array because arrays are supposed to be a fixed block of memory with a fixed length, but it's a dynamic thing, like the thing we call array in JavaScript. You can keep adding elements and keep appending it, and it will increase the size on the flow itself. So it's ideally a list or something, but people call it array, so let's call it an array. But ideally, that's not how an array behaves. Array by definition is a fixed block of memory with fixed length. That's all. So let's take an array. Let's take array, and we have this here, right? So what we are doing is we have 10 to the power 7, we have I equals to 0, and we are pushing this. So this is it has 10 characters, 2 bytes is, so 20 bytes per string. So the total memory it will consume is 20 into 10 to the power 7, roughly. So I have 39% of memory currently being used. So if I try, let's increase it a bit. I think it won't be significant enough. Let's do 10 to the power 8. So if I try to pull this, if I try to insert this in memory, you will see there's a spike. It went till 42. So almost 41, settled in 41. That's it. So that's like 2% of memory, and I have 32 gigs of memory. So that's a lot. So it consumed that memory, and it's not releasing it, as you can see. It's still consuming it, because if it would have released it, then this would have gone down to the initial percentage. Like, of course, there are many constraints here, and it's not an isolated device, so these metrics are not accurate as such, but you can approximate it, right? So it should go down by some amount at least. But ideally, when you do such benchmarking, it's good to have an isolated machine where you don't have any other resources running as such. so that you can get the exact raw numbers, but we don't need that for this use case or for this demonstration. So how will you release this memory? In JavaScript, there is something called garbage collection. So garbage collection, we'll come to that eventually, but roughly what garbage collection does is, it will scan through whatever you have in your program and whatever you have in your applications and such, and whatever is not using memory, it will release those for other things to use. But here it's not releasing it. So let's go to memory, performance, and here is a dustbin icon here to collect garbage. And if I click on this, it should release the memory back to what it was. Yep. So let's try this again. Let's put it in memory. It should spike up till about 41, went till 42. Yeah, that's what I said. Because it's very unpredictable with these kind of devices to test on, because there are many things running. So these benchmarks are affected a lot by those aspects. But roughly our demonstration is roughly we made our point with this. This is enough for us to draw a conclusion from this, that it's memory intensive. Now let's go to performance and clear it, and it will go down to whatever it was. Cool. So this is a memory intensive operation. That was a CPU intensive operation. So these are the two extremes of the line. So any approach that you take should lie, let's say it's very CPU intensive, try to push it towards the middle. Try to make some use of memory and make it a bit faster, make it a bit efficient. If it's consuming a lot of memory, try to push it towards maybe using some amount of CPU, because that's a resource that you have available, right? So maybe use that a bit, otherwise it will just sit idle, right? So you have to use both efficiently, and you have to get the maximum out of whatever you have. So that's the perspective that I wanted to give. So other than that, let's take an example of two extremes of things, right? Let's take the example of what we discussed initially about the capital of a country. So let's say, I mean the second example will be better. Let's say I have a program that multiplies two numbers and gives us back whatever it calculates. On one extreme we have CPU intensive operations, right? So if I go to this extreme, if I take the CPU intensive approach, what I would do is, for every single request I get, I'll calculate every single, I'll multiply both the numbers every single time I get a request, and I'll send a response. Let's say someone is making a request to multiply 69 and 420 a million times. I'll do it a million times. So I'm not even using my memory much. It's very underutilized, but your CPU is overutilized. So that's not a good approach, right? You have to bring it towards the middle. So for every calculation, you are calculating the same value again and again and again and again, and passing it to the user. So that's the CPU extreme of the approach. The memory intensive approach would be, for every possible number, let's say we are confining, let's say we had a constraint, let's say we are confining it to 3-digit number, the last number that someone can enter is 999. So for the most memory intensive operation would be, for every possible combination of two numbers, what you get in from 0 to 999, you put everything in memory, which is of course not a good approach, but I'm talking about the extreme approach of it. You put every calculation in memory, 0 into 1, 0 into 2, so on till 0 into 999, then 1 into 1, 1 into 2, so on till 1999. So you are putting everything in memory. What's bad with that approach is, it will take up a lot of memory, first of all, which is, debatable, but still, let's say, because there won't be that huge number of combinations, but let's say it takes a lot of memory, right? So here what we have is, it's taking up a lot of memory, and you won't be even using much of it, right? Because something very obvious, let's say 0 into 1, it's very less likely that some user will make that request, because they can calculate it inside their head. Anything into 0 is 0. So, but you are storing 999 blocks of memory as such for that particular use case, right? So that's not even used much. Another case could be, let's say someone is requesting 69 and 420 a lot of times. You are giving that and 0 into some XYZ the same priority, which doesn't make sense, because those are not very much used. This is very frequently accessed. So one good approach is somewhere in the middle, right? So let's say there is some combination which has a huge number of requests. So what you do is you calculate it once. Let's say if there are frequent requests, you calculate it and put it in memory for that particular value, so that from the next request it will start from the memory. It won't go back to the CPU next time. But for calculations that are not done that frequently, you don't need to store it in memory. It doesn't make sense. So that way you are saving a lot of CPU intensive things by storing in memory, things in memory, and then you are also not overusing the memory as such for unused things that are not required as such, right? So that's the logic behind caching only. That's how caching is done. So the most used resources, people store them in memory and then pass it from the memory to the user. Not everything in memory, not everything in CPU. So that's the middle approach of it. So that is sort of an approach that people take in production as well, because that's optimized. So basic approach to solving any problem that's focused on a limited number of resources, you need to utilize both of the things properly. You cannot push one extreme and leave the rest idle, and same for the other side. And there is tug of war between memory and CPU always. You will see this everywhere. So the basic purpose of this video was to first of all build an intuition of what can consume a lot of CPU, what can consume a lot of memory. By seeing at the problem, you should be able to somewhat predict, if not exactly, that it's consuming a lot of CPU and it's consuming a lot of memory. And second thing is to, if it's like, try to push your approach to the middle, that like, so that you are making a good use of both the resources that you have, right? So yeah, now in this case, the Fibonacci thing we discussed, right? So let's take our approach that takes up both CPU and memory, right? It takes up CPU, it takes up memory as well. And let's see how far it can optimize the old approach that we have. I mean the old approach that we had, right? So here we have this. It is, I named it Fibonacci optimized or whatever. So we have like an initial array with 0 and 1, and after that for n we are just adding it with the previous value n minus 1 and n minus 2 at value, and putting it in the, like, sorry, not n, I minus 1 and I minus 2 at value, and putting it in the ith index of it, right? So that's the Fibonacci series. Like, you go one step back, you go two step back, add those and put it in the current value. That's the Fibonacci series. So that's what you are doing here, nothing complex as such. So we have 40 iterations, or n equals to 40 here. So before this, let's try with the old approach, right? This was the old approach. Let's try 43 only. Let's see how long it takes for us to calculate this. You can see it took us like 3 seconds to calculate this. Now let's try it with the new approach. It's doing the same thing, right? It's nothing different. But let's try putting 43 here and see how long it takes. It was instant. It didn't even take like 1 second, even less than like one. It's some 1000x, 3000x, or x, like faster, a lot faster, because we are not doing the things repetitively here like we are doing here. Here we are taking help of memory to remember things and then using those to calculate or come up with a final value of it, right? So this is the difference that it can make. Like, if you have the same resources here, right? If you were to focus on, let's say, my program works and I don't need to do anything about it, that's fine, leave it. Like, there's this famous thing in tech where people tell, if it works, don't touch it. Like, that's a shitty quote. I don't agree with that, because if you were to do this here, because you can see both of them are correct, both of them give the same answer, but the thing is, you don't have infinite resources. You have to make good use of what you have, and you have to use them efficiently so that you can do the same things faster. So understanding that is a very important aspect of day-to-day like coding and stuff, because things like this, I come up across a lot of things that's similar to this, which are not optimized, which we can optimize, and so on. So understanding how a CPU works, how memory works, when to optimize for what, it's very important. Okay, so yeah, that's the basic thing, like that's the basic intuition, or that's the basic purpose of this video that I wanted to make. And yeah, so like, learn to use the resources efficiently, always keep track of this line. Your approach should generally speaking be somewhere in the middle for most of the times, not always. It's not a very like written in stone sort of a law, but for most of the times you can find an approach which somewhere falls in the middle so that you can use both your resources efficiently. So yeah, that's all for this video, guys. If it helped, then maybe drop a like, share it with your friends, and if you have any questions you can ask in the comments, of course. And yeah, see you guys, bye.